what I'm going to do with these examples now, I'm going to break it down by each part. So we're going to first find the vertical. We're going to find the vertical asymptotes and holes of the examples that we have in example 24. So we're going to start with these first because domain restrictions are relatively easy to find. So here for A, I'm going to first factor. I get x plus 3 over x plus 3 times x minus 3, which means my domain is all real numbers except negative 3 and 3. My restrictions are negative 3 and 3 for x values. Those two restrictions are going to define either a hole or a vertical asymptote, each one. How do I know which one it is? If I look at what I have here, x plus 3, I have one on top, I have one on bottom being multiplied, therefore I can divide those out and they can cancel, leaving me with an expression of 1 over x minus 3. So the x plus 3's cancel each other out. Now they're gone, but they're not forgotten. That means, the negative 3, which was a domain restriction because the x plus 3 was in the denominator, is still a domain restriction. However, because it's essentially been removed because of a cancellation, it's what we would call a hole. That's why in calculus they refer to a hole as a removable discontinuity. Therefore, my hole is at x equals negative 3. Now, the reason why I came up with this more simplified expression over here is because for me to find the y coordinate of that hole, I'm going to plug the negative 3 of x into that expression. If I plug it into the original, I'm going to get 0 over 0, which is going to be something else we talk about later with limits. But here it means, okay, well, I will get 0 over 0, which means I get more work to do. So once I have it broken down, I plug negative 3 into this, I get 1 over negative 6, which is a negative 1, 6. So the hole is going to have coordinates at negative 3, negative 1, 6. Going to B. Again, I'm going to do the vertical asymptotes and holes for both of them. Now, the vertical asymptote is going to be x equals 3 because that issue has not gone away. X equaling 3 is still, even after the cancellation, a domain restriction. So the vertical asymptote is going to be at x equals 3. For part B, again, a good idea for you to look for these things is the factor, because you want to see, what numbers would make the bottom 0, and having it factored would certainly help with that. And also you want to see if there's any cancellations that could happen to see if there's any holes. Again, factoring is going to help with that. But if I go through there and do the factoring on the bottom, I get 2x minus 3 times x minus 4 on the bottom, which means that x cannot be 3 halves or 4. Those are my domain restrictions. So 3 halves is going to be either it's going to be a vertical asymptote value, or it's going to be the x coordinate of a hole. And the same thing with 4. Again, now I look at this expression now in factored form. The x minus 4's would cancel. I'd be leaving with an expression of 4x plus 1 over 2x minus 3. If I were to graph the original function and 4x plus 1 over 2x minus 3 on a calculator, you would see no difference whatsoever. Okay? It'd be exactly the same. It would only be when you look at the table of values would you notice a difference, because if I look through the table of x versus y values, and at x equals 4, if I had the function as h of x is written right there in there, I would see an indication it's undefined there. Whereas if I had y equals 4x plus 1 over 2x minus 3, at x equals 4, I would see a number over there, and of course that number would be the y coordinate of our hole here. So since the x minus 4 cancels, x equals 4 is where there is a hole. So the hole's going to be at 4, comma, h of 4. So I put 4 into the original function. Now, not the original, the new function, 4x plus 1 over 2x minus 3. I get 17/5, which is about 3.4. So the hole's at 4, comma, 3.4. The 2x minus 3 did not cancel, which means that x equals 3 halves is the vertical asymptote. For C, g of x equals this stuff here. Again, I'm going to do some factoring. The top factor is into 2x squared times x minus 2. The bottom factor is into x minus 2 times x minus 2. I only have one domain restriction. x equaling 2. Because if x equals 2, both of those x minus 2's in the bottom are going to become 0, and 0 times 0 is 0. I don't want it down there. So any number but 2 is the domain. I do have a cancellation of of a set of x minus 2's here. So the one I have on top cancels with one of the ones I have on the bottom. It leaves me with 2x squared over x minus 2. The question that comes down to is this. Is x equals 2 a whole, or is it a vertical asymptote? Well, I have a cancellation, so a lot of people think it might be a whole. But the fact of the matter is, I have to ask myself the question I asked myself the other two times. Is x equaling 2 still a domain restriction on my simplified my simplified expression? And yeah, it is. I still have an x minus 2 in the denominator. 2 would still put a 0 in the denominator. Therefore, it's not going to be a whole. It's going to be a vertical asymptote. So that's what I have here. Now getting to these ideas again. We've talked about these really briefly. Again, when I look at I'm going to look for the highest powers of x on top and bottom. And if I notice that the highest power of x is on the bottom, y equals 0 is my horizontal asymptote. If I have the same highest power of x on top and bottom, the ratio of the leading coefficients will be my numeric value for y equals for my horizontal asymptote. And if I have the higher power of x on top, that's an indicator of an oblique asymptote, which I'm going to have to find the equation for. So let's take a look at what we have here. So for A, we got this far with our vertical information. I'm going to look back at the original function when it wasn't factored. And if I look at this, my degree in the numerator is 1. My degree in the denominator is 2. So I have a higher degree in the denominator. Because of that, the horizontal asymptote is going to be at y equals 0. When I look at the original h of x, the highest degree on top was 2, the highest degree on the bottom was 2. Therefore, my horizontal asymptote for this is going to be the ratio of those leading coefficients. So y equals 4 over 2, or 2, so y equals 2 is going to be the horizontal asymptote. For g of x, I have a higher degree on top than I do on bottom. That means I'm going to have an oblique asymptote. And what I'm going to need to do is carry through the long division. So you see what I did down there. I'm not going to go through it by step, but what I did is I took the 2x cubed minus 4x squared. I put the plus 0x plus 0 in the for placeholders and divided it by x squared minus 4x plus 4 and got a quotient. I don't care about the remainder part. The remainder part is worthless to me. I just want to see what I end up on my long division symbol whenever I'm done. I can't do anymore, because that's going to be the right hand side of the equation for my oblique asymptote. So y equals 2x plus 4 is my oblique asymptote. So this gives me some information about how to draw these things, but it's limited information. So if I go back to example A, here's my graph, and here's what I know so far. I have a vertical asymptote at x equals 3. I have a horizontal asymptote at y equals 0. And I have a hole at negative 3, negative 1, 6. That's all I have. So I have two things that are features that the graph is going to tend to avoid. And I have a hole which really isn't even on the graph. So I really don't have anything that's on the graph except the hole will be along the path of the graph. That's one thing you have to be aware of. A hole is always going to be along the path of the graph. You're not going to have a situation for these where you have a graph doing this, and then you're going to have a hole like up here somewhere. It's not going to work that way. Okay, so make sure that the hole is along the path of the graph. So I could kind of count that hole as a point, but it's technically not a point. So what I want to do is I want to get some x and y values to allow me to get an idea of what this really looks like. So I use my vertical asymptote, or if I have several, I use them as my centers, so to speak. And so 3 is going to be my center for my graph. So I pick some values bigger than 3, one close by, one further away at the very least. I pick some values that are smaller than 3. You notice I included negative 3 up there with a circle around it because that's where my hole is. So I chose some values that are bigger than 3, some values that are smaller than 3. Some that are closer to 3, some that are further away from 3. And I'm just going to take those values and plug it into the original function, get some x and y values. And when I get those x and y values, of course at 3, the y value is undefined. At 3, negative 1, 6 is actually undefined too, but it's a whole. But I plotted those other points, drew the graphs through them, and also tried to avoid the asymptotes, and that's what the graph would look like. Now on a calculator, you're not going to see a little indication of a hole. A hole, you have to remember, is infinitely small. The only way you're going to notice a hole is if you go on your calculator, go to the table feature, and you'll see like for that specific value, it's undefined. So be aware of that, but the graph will look exactly like this with the exception is you won't see that open circle shown up on your graph. For this one here, same kind of thing. I mean, I have, a graphing region here. I have a vertical asymptote of x equals 4. No, sorry, x equals 3 halves. I have a hole at 4, 3.4. I have a horizontal asymptote at y equals 2. So I have this information. Again, it's not a whole lot. So I need to have some additional points to plug in order to get an idea of how this is shaped. So again, I'm going to use my vertical asymptote as a center. So 1.5 is the center. I picked some values bigger than 1.5 and some values that are smaller than 1.5. I also included 4 in here because I know that's where my hole is. So again, I'm going to plug these numbers into the original or you can actually just plug them into essentially the more simplified version of it, because it's again the two graphs are identical looking. So any point that's on h of x is also going to be on 4x plus 1 over 2x minus 3, except for the hole that we had in this problem. So I plug them in, I get these values, I connect the dots, I try to avoid the asymptotes. That's what you get. This one here, again, same kind of situation. All I really have from the information here, no hole. I have a vertical asymptote at x equals 2. I have a oblique asymptote at y equals 2x plus 4. So those are those two lines. Again, these are features that my graph's going to avoid, but it really isn't a graph. So I got to find some points to put on this graph. So again, excuse me, I'm going to use my vertical asymptote as a center. I'm going to pick some values that are more than 2 and some values that are less than 2. You don't have to pick as many as I did. I just picked those numbers just to have more of a variation. But I want to make sure I pick at least one value that's close to the vertical asymptote value and one that's definitely farther away. So I picked those values, plotted them, and that's what it would look like. And these graphs are pretty accurate, not having to get a whole lot of points. So again, this procedure is to let me focus on the area where most of the quote-unquote interesting stuff is happening so I could graph an accurate picture of it.